Hello and welcome back to Calculus2, section 7.3 on hyperbolic functions. Now, this has a lot of stuff in there, therefore we're probably going to do this in two separate videos, two separate lectures. The first part is the definition, pre-calculus portion, meaning what they look like and what they do. And then the second part would be the calculus, meaning derivatives, integrals, and all that cool stuff. Now, I'm going to start this with a statement in blood, written in blood, which says hyperbolic functions are not trig functions. So I've seen a lot of students make this mistake where they regard hyperbolic functions as trig just because of the name. I'll explain why they're named the way they're named, and you'll see some of the properties will be identical and very similar and so on. The basic property of trigonometric functions is the fact that they are periodic. Meaning, you wait a little while and it repeats itself. Sine function has a period of 2 pi. It's that squiggle, right? And then every 2 pi, it will repeat exactly the same squiggle. The difference between the blue light and the red light is simply the sine function is squished more, right, for the blue light. So it has a different wavelength, meaning the period is different. So we have these periodicity rules for all 6 trigonometric functions. Hyperbolic functions are not periodic at all. Therefore, they are completely different type of functions. Now, why the names then? See, hyperbolic functions will be called sine hyperbolic x, cosine hyperbolic x, tangent hyperbolic x, cotangent, secant, right? All of them, all 6. So why the names if they have nothing in common? Well, the behavior of these functions is, in terms of identities and some other things, turns out to be very similar and reminding of trig, even though they have nothing to do with trig. Now, to get into the hyperbolic functions, I'm going to write something that is out of the scope of what we do here in terms of real calculus. So in mathematics, you know, you have real numbers and then you have imaginary numbers, and when you mix the two, you get complex numbers. So long time ago, over 300 years ago, one of the gods of mathematics, Leonhard Euler, figured out the relationship. Well, he figured out pretty much all mathematics we have, branches and so on. He figured out that the connection of sine x and exponential function e to the x. So he figured out that you can write sine x as e to the ix minus e to the minus ix divided by 2I, where this I is the square root of -1, which is the complex imaginary I. So he wrote this. He also figured out that the cosine x is the same e to the ix plus e to the -ix divided by 2, no I for cosine. And all of the identities that you can do with sine and cosine, they would work if you use these. Now, obviously, algebra is much messier. You have to do a lot more calculations, computation, but the results would be the same. And the reason why it's periodic is this I, because I tends to loop as you apply powers to I. I to the first power is just I, but I squared is -1. I cubed is negative I to the fourth is +1, and then I to the 5 loops back to be I to the 6 is -1, I to the 7 is negative I to the 8 is +1, and then rinse and repeat forever. So as you take exponents of I, they will go into this group of 4, and they will keep looping. Now you can immediately see this feature when you start taking derivatives of sine. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine, and then derivative of negative cosine is positive sine. Loop of 4, go back to the original value of sine. You take another 4 derivatives, loops back to the original sine. So if you take the derivative of sine and cosine, they will also loop in the groups of 4. Well, that's courtesy of the I that is in these, that is floating around these exponentials. Now you know that derivative of e to the x is e to the x, and then you just have these i's following all over. So now if you are more adventurous, you will obviously take the derivative of the right-hand side just to show that you get the expression below, keeping in mind that I squared is -1 anytime you have to calculate that. So you see that sine x and cosine x can be written this way, and Euler, being the genius he was, he just said, well, what happens if I just remove i's? What happens if I just say e to the x minus e to the minus x over 2? So if I just go in and erase all the i's, and he immediately, right, this is how he has created a whole bunch of mathematics, just basic exploration and having these ingenious thoughts. For most of his life, he was blind. So he was just dictating mathematics to a bunch of scribes that were sitting around this table. And he is, to this day, the most productive mathematician who ever lived. There are volumes and volumes and volumes of books. He was pumping few papers a week of how much stuff. He coined all of the trig and all of the hyperbolics and all the exponential. E is named after him because Euler, right? That's E, so the limit definition for E and all of that stuff, that's all him, including a whole bunch of, and you probably saw that equation e to the I pi. Have you seen that one? E to the I pi equal to 0, plus 1 equal to 0. That's one of the most famous equations ever written, considered to be the most beautiful equation in all of mathematics forever, because it connects all of the cool values that we know. It's 1 and 0, and then e, I, and pi. Anyway, so that's all him. So that's what he did. He said, what do I get? And he worked out in his head the entire lesson today, right? He worked out in his head and said, yep, that's cool. So we're just going to call these hyperbolic functions. Now, hyperbolic functions, you see, you get your sine and cosine, and those sines and cosines, eventually you will see, you can use in parametric equations to create circles and ellipses. Well, it turns out that if you use hyperbolics, you create the inverses of ellipses, which are hyperbolas. So they do have a very painful explanation of that stuff, literally going around the point, because they can't make a point because you guys haven't learned parametric equations yet. So these equations, sines and cosines, are related to circles and ellipses. Well, circles are special ellipses, so you can just say ellipses. And then hyperbolic sine and cosine will be connected to hyperbolas. So now we get to the first definition of the day, well, first two definitions of the day, where we say that sine hyperbolic x, so now this SINH is one unit, and then followed by the argument. So SINH is one word standing for sine hyperbolic, and then x is the argument of it, which is separate. So sine hyperbolic is defined as e to the x minus e to the minus x over 2, and cosine hyperbolic x is e to the x plus e to the minus x over 2. So as you can see, the same without i's. Now, from here, you get to work out the other four. Tangent will be defined as sine hyperbolic over cosine hyperbolic, and you can work out the algebra. And all of the others work the same way. So now, tangent hyperbolic x is sine hyperbolic x over cosine hyperbolic x, which would be e to the x minus e to the minus x divided by e to the x plus e to the minus x. So that will be tangent hyperbolic x. The 2's will cancel when you divide them, right? Cotangent hyperbolic x will be cosine hyperbolic x over sine hyperbolic x. And by now you're going, this is the same stuff as trig. Yeah. But it's not trig. So when you divide them, you still get expression with ease on the other side. Secant hyperbolic x is 1 over cosine hyperbolic x, so that's going to be 2 over e to the x plus e to the minus x. And finally, cosecant hyperbolic x is 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. Now I'm going to box these ones as well, but they are of lesser importance than the top two because we use top two to derive everything else. So now that you see all of these functions, you see that they are defined in terms of exponential, right, e to the x and e to the negative x, and then combinations of those. So now, when you are considering these functions, you might be interested in their graphs. And these graphs, these functions are featured in your TI 8384 if you have one, or you can just look it up online. But you have to use the catalog button on 0 to reach the hyperbolic sines and cosines. So you would go into second 0, which opens the catalog, and then you would scroll down until you get cosine hyperbolic, let's say. Or you can use alpha C to jump. Second catalog, alpha C. There we go. And then go down to, so if you take a look at your screen, you will have cosine, cosine inverse, cosine hyperbolic inverse would be on the list. So you select your cosine hyperbolic, let's say, and then you say of 5. And it's going to give you 74.2. So you can use calculator to compute values. You just have to go on a catalog. It will give you sine, cosine, and tangent hyperbolic. I don't think the other ones, because you can just do 1 over for the other 3. All right, so now let's take a look at the six graphs. Hyperbolic function graphs. I'm going to get the image for this. Get this as best. Okay, open in a new tab. There we go. All right. So here on the screen, I can, draw this. But here are all six. I will draw this as well. And do we see periodic behavior on any of these? Meaning, wait a little while, it will repeat itself. The answer is hell no, right? There is no periodicity, therefore these functions have nothing to do with trig. All of the trig functions repeat after a period, right? So now when you look at this, the first one reminds you almost of x cubed. The second one reminds you almost of x squared, right? The third one reminds you of, if you know inverse tangent, looks like inverse tangent. The one on the cotangent hyperbolic looks almost like 1 over x, right? The bell-shaped curve on secant hyperbolic, and another 1 over x for cosine hyperbolic, right? So these are your, for cosecant hyperbolic. So these are the six, and you are going to find some use in probability over here, but the most use, and if we have any electrical engineers in the house, your cosine hyperbolic, if you're doing high power, when you have two power towers with a wire stretched between the two towers, that's the sag you get between the two. You do not want to stretch the wire from one tower to another in a straight line because, anyone? Why don't, because, right, if you stretch it, then you're going to use less cable, and that stuff is expensive, times 5 wires, right? Why don't you want to stretch it straight through and save on length? Well, you have tension anyway because it's a good try, but it's not tension. Very tricky to think of those things because you're not high-power electrical engineers. Right? What happens with objects when they get very, 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 very cold? Yeah, they shrink, right? So you have to have some sag in it. Otherwise, in the winter, right, if it's stretched, it's just going to snap everywhere, right? Now, if one side snaps, then all of the tension is on the other side. It's going to rip out the tower. Now, those towers are $100,000 each. One tower plus one set of wires on one side. I'm talking about those big towers. I'm not talking about those little wood towers. I'm talking about those huge towers that have 100 kilovolt leads and stuff like that. It's $100,000 per tower. Now look how many you have down the line, right? If you count 10 towers, it's $1 million, right? So as an electrical engineer, you have to actually use differentials. Yay! You have to use differentials. And this cosine hyperbolic to calculate the sag, right? So you know. Now, can you just eye it? Well, of course not, because what happens in summer when it's very, very hot, plus the load? It expands, right? So what? You're going to have it now over the highway, right? Cutting every car in half as it passes through, right? No. So it is a very precisely calculated sag, which is modeled by cosine hyperbolic. So anytime you take any kind of wire and stretch it between 2 points, it's not x squared, it's cosine hyperbolic. So it's useful. So that's the most used hyperbolic function in application. And then, so even for the bridges, if you have that big, like very thick suspension bridge, that's going to be cosine hyperbolic. And you should have few of those word problems in there. And you have, as I mentioned, your bell-shaped curve over here. So that can be modified and worked on to get some of that stuff out of it. So let's just sketch real quick. So the first one looks almost as x cubed. It's not x cubed, but that's what it is. So that's the sine hyperbolic x. Then we have our cosine hyperbolic x, which is, as I said, the cable. Then we're going to have tangent hyperbolic x is going to look very similar to the inverse tangent graph. Very similar to, well, let's put it here. It has these asymptotes, so it doesn't actually follow. There are asymptotes in positive 1 and negative 1. So it's not like 1 over x, but it's close, which is the cotangent hyperbolic x. And finally, secant hyperbolic x looks something like a bell-shaped curve. And at the end, this looks almost like 1 over x cosecant hyperbolic x. None of these are periodic, right? None of these are periodic, and you can look at these and figure out their domain and range by staring at the graph. So sine hyperbolic has both domain and range, all real numbers, because it stretches infinitely to the left and right, and it stretches infinitely up and down. So domain and range are all real numbers. Cosine hyperbolic starts at 1 and goes up forever. So your domain, which is left and right, is infinities, and your range, which is the y values, start at 1, go to positive infinity. So you just use your eyes and you look at them, and you will know. Now, for the tangent and the rest, you can start dividing these functions to see where they land. So once you see the graph for these functions, you would know. From there, you have your x-intercepts, you have your y-intercepts, you have your asymptotes. So all of that good stuff, well, domain, range, right? So all of that basic stuff from pre-calculus 1. You shift these functions the same way. If you add like plus 1 at the end, then the whole function raises up, right? And goes to 2 in this case. So all of the shifts are preserved because the shifting of functions and function reflection, which you learned in pre-calculus, is applied to all functions, not just at the limited amount of functions you knew at the time. There's a book with 2,500 pages in it called Mathematical Functions. 2,500 pages. You know what the polynomials take? 1 page. All right? Now, polynomials have infinitely many applications so far for you. You have the constant, linear, quadratic, cubic, right? They're all listed as separate functions. They're not separate functions. They all belong to the polynomial, to the realm of polynomials. They take 1 page in that book, all right? Trig takes 1 page in the book. 2,500 pages of mathematical functions. You haven't even scratched the surface of what you have seen with absolute x and sine, cosine, ln x, and all of that stuff. Not even scratching the surface. And we are adding 12 today. Also 1 page in the book, right? So what we are doing here is, looking at the graphs, figuring out all of those basic properties of pre-calculus, which are domain, range, x, y intercepts, and asymptotes. And then the blue box over here hinted that some of the properties that are true for trig, hopefully slightly modified, would work for these guys. And yeah, that's true. So what we get is the list of these, I believe, 10 identities. 12 identities on page 504, which we can prove by substituting e's for sine hyperbolic, cosine hyperbolic, and then just working out algebra to prove those identities. So those are some of the cool problems that you can have on the test. So let's say, well, let's first list those hyperbolic identities. And I am going to solve one, and then I'll ask you to pick any one you want. I'll solve that one as well, which leaves you with another 10 to enjoy at home and possibly see on a test. So number one on the list, cosine hyperbolic squared x minus sine hyperbolic squared x is equal to 1. What is the trig one with squares that gets you 1? Sine squared plus cosine squared is equal to 1, right? So you see over here is cosine hyperbolic squared minus sine hyperbolic squared gives you 1. $1 million to the person who knows what this one is. If you are just doing this, what is this equal to? Yes! Ding, 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 $1 million. See, look at that. He's rich for another 5 minutes. This is how long it takes to spend $1 million. Right? Look at that. Ouch, right? Now these hyperbolic ones are going to start messing with your head. If you are bad on trig, then this is going to make you worse, right? Because they don't line up. But they have the same form. So welcome to hell. Let's crank the temperature with number 2. One minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. I don't want to ask what's wrong because it's correct. What's the trig one? 1 plus, exactly. You see, they are so damn close without being exactly the same, just enough to mess it up, right? So hyperbolic has a minus there. The trig identity that you will need for your section on trigonometric integration and trig substitution, which is next week, is going to be 1 plus tangent x equals secant x. So it's at least they are pairing sine and cosine hyperbolic and then tangent and secant. That's at least the pairing is the same, even though the formulas are so. And here's another one with a cotangent hyperbolic squared x minus 1 is equal to cosecant hyperbolic squared x. Again, it's the same issue with the plus 1 for trig and minus 1 for hyperbolics. Okay, now is this the, no, this is not the, well, I can put them in the correct order and then, okay, so breath of fresh air on sine hyperbolic x plus y. This one works the same way as trig, right? So sine hyperbolic x cosine hyperbolic y plus cosine hyperbolic x sine hyperbolic y. So yoo-hoo. I'm still keeping this. I'm just going to move it. Number 5, this is under, here we go again. Cosine hyperbolic x plus y, cosine hyperbolic x, cosine hyperbolic y, plus, at which point you can rage, sine hyperbolic x, sorry, yeah, sine hyperbolic x, sine hyperbolic y. That sign is minus for trig, right there. And here it is, under 6. Cosine hyperbolic 2x is equal to sine hyperbolic squared x plus cosine hyperbolic squared x. Now, if this is not making you rage, I don't know what will. Do you see that these two damn formulas are completely swapped for trig? Right? Sine squared x plus cosine squared x gives you 1, and my cosine squared minus sine squared is supposed to give you cosine 2x. They're completely swapped. Right? They're answers. So you really need to pay attention which one is which, because they're so close yet completely, as you can see. So the only one that looks exactly the same, so if you are to go and erase all ages, would look the same as the trig one, is number 4 so far. Everything else has something that it's off, either a sign or a conclusion is from completely different formula in comparison to trig. Number 7. There it is, sine. This is sine hyperbolic 2x is, well, this is going to make you happy. 2 sine hyperbolic x cosine hyperbolic x. So this is another one of those where if you are to delete all ages, you get trig formula verbatim. And 8 and 9, extremely important formulas, power reducing formulas. Remember that you have sine squared, cosine squared power reducing formulas, and if you don't know them, you can't integrate. Well, now you have the 2 for this. The good news is, well, they're very close. They're not the same. The good news is just swap the numerator and you got it. So cosine hyperbolic squared x is cosine hyperbolic 2x plus 1 over 2. And number 9, sine hyperbolic squared x is cosine hyperbolic 2x minus 1 over 2. Now your trig identities are 1 plus cosine and 1 minus cosine, so they just swap. Now obviously for addition, it doesn't matter which one is listed first, so number 8 is still the formula that if you are to erase ages, you get exactly the same as trig, but the one on the bottom, you actually have to swap the terms over here in order for it to work. And finally, the last 3 are the ones that talk about even and odd functions, where we learned that the cosine is even, which is the same for trig. Cosine hyperbolic is even, and the sine and tangent are odd. So number 10, 11, and 12, should do this blue. So number 10 says that the cosine hyperbolic of negative x is the same as the cosine hyperbolic of x. I'll put in parentheses even function. And we have 11, sine hyperbolic negative x is equal to negative sine hyperbolic of x, odd. Now this follows exactly what trig has, which is good. And tangent is also odd for hyperbolics, just like the other ones. So all 3 of these, if you are to erase ages, they work exactly the same as in trig. Also odd. Now, does this mean that we don't care about the other 3? Well, the other 3 are combinations of these, and you know what happens when you divide even with odd, or odd with even, and all that stuff. So we can get. So this is the list of 12 identities, and there are problems in the book, in the homework, which ask you to prove more complicated identities using the simpler identities. But before you get to prove any of those identities with these, you need to know how to prove each one of these. And you prove them simply by working with E definitions. So let's take a look at number 6, because, right, with the cosine, because that's the one that, right, you would like to be 1, but it's not 1, right? So prove cosine hyperbolic 2x is equal to sine hyperbolic squared x plus cosine hyperbolic squared x, right? You would love for this to be 1 because it will be the same like trig, but it's not. It's this. So how do we prove it? Well, we start from the right hand side. We know that sine hyperbolic is given with e to the x minus e to the minus x over 2, and I have to square that, and I have to add to that e to the x plus e to the minus x over 2, and I have to square that. So this is the right hand side, and now I'm just going to work with these values, just work out a whole bunch of algebra, and hopefully it simplifies into something that I can compress into a cosine of 2x. So the first order of business is to square these. So when you square, you have the square of binomial, so you have to get 3 terms. So you get e to the 2x minus 2 times e to the x e to the negative x, and then plus e to the negative 2x divided by 4. Plus more algebra on the second one, e to the 2x plus 2 times e to the x e to the minus x, and finally plus e to the negative 2x divided by also 4. 2 squared is 4. Now e to the x times e to the negative x is e to the 0, which is 1. So all we get here is e to the 2x minus 2 plus e to the negative 2x divided by 4 plus e to the 2x plus 2 plus e to the negative 2x over 4. Well, you have the common denominator, just add them, right? So common denominator is 4. E to the 2x plus e to the 2x is 2e to the 2x. Plus 2 and minus 2 cancel out. And you have plus 2e to the minus 2x. You factor 2 and cancel with 4. So 2, 2, and 4 cancel. You get a 2 on the bottom. And you get e to the 2x plus e to the negative 2x over 2. And this is the definition for cosine, right? Definition for the cosine has a plus. But look at the exponent. Exponent is no longer x. Exponent is now 2x, which is why this is cosine hyperbolic 2x. Whatever the exponent is what the argument of the cosine hyperbolic. Does this make... I mean, I can make it ridiculous and it's going to click immediately. Sure, why not? So, orange, purple, orange. Cosine hyperbolic of a heart is equal to e to the heart plus e to the minus heart divided by 2. It doesn't matter what you stuff in here, it's going to be the same on these exponents. So if I have x, it's x. If I have 2x, it's 2x. You have to have the same exponent on both in order for it to work. Now, if you don't like heart, put a flower or whatever. Doesn't matter. Good. Now you get to pick one from the list of identities, and I'll work out another one. And then we're going to take a look at some of the identities that need to be proven from the book. So is there anything that you like / don't like? I already did 6. So anything else? including the 3 on the bottom with even and odd. Oh, please don't all scream at once. Yes? Number 5. Cosine of x plus y? Cosine hyperbolic x plus y? Okay. Prove cosine hyperbolic of x plus y is equal to cosine hyperbolic x, cosine hyperbolic y, and then we have a plus. For the trig, it will be a minus. For hyperbolics, we have plus. And then sine of both. So sine hyperbolic x, sine hyperbolic y. Now, for this particular identity, you have to replace both sides with e, and then hope that once you work out all of the algebra, that the left side will eventually equal the right side. So for the left side, I have e to the x plus y plus e to the negative x plus y divided by 2. So that's the left-hand side. And remember, whatever the argument is, that's what the exponent of e is. And then one is positive, one is negative. It's cosine, so we are using a plus over here. Now, on the other side, please make sure you stretch your wrist, because the carpal tunnel is something that you are going to definitely develop by the end of this problem. On the right-hand side, we have 4 of those fractions to deal with. So the first one is e to the x plus e to the negative x over 2 times e to the y plus e to the negative y over 2. Plus, and now we have signs, those have negatives in between e's. So e to the x minus e to the negative x over 2, and e to the y minus e to the negative y divided by 2. So the first step was to replace the left and the right side by e's. And now I just need to, simplify all of this algebra here, hoping it will land into this. So let's go and focus on the right-hand side only. Well, I get to multiply now, right? Or as you would say, FOIL. So e to the x times e to the y. Please remember, here I'll write it in blood, a to the m times a to the n is a to the m plus n. This is basic algebra 1. So when I multiply e to the x times e to the y, I get e to the x plus y, which is, woohoo, right there. So, first off, I have the denominator, which is 4, that's cheap. And now multiplying here, I have e to the x plus y plus e to the minus x plus y. So that's both of these being multiplied by e to the y. Now I have to switch and multiply by e to the minus y. So that's going to be plus e to the x minus y, and finally plus e to the minus x minus y. So when I multiply the first two, I get these. Now, none of them are like terms. None of them combine together. Plus, and now I have the second one. Right, 2 times 2 is 4. And we go do the same thing. So we have e to the x plus y minus e to the minus x plus y minus e to the x minus y, and finally plus e to the minus x minus y. Now if you take a look, you will see minus x plus y, minus x plus y. This term is positive, that term is negative. So they cancel as the orange pair. And then e to the x minus y and minus e to the minus y, they will cancel as the blue pair over here. They cancel because they subtract to 0. So you're left with e to the x plus y plus, and now I'm going to factor out negative. I'll have e to the negative x plus y in parentheses. Everything divided by 4. Oh, that looks almost exactly as that one. The 4 over there is messing things up. Let's see what we get on the other one. Well, the same thing. E to the x plus y plus e to the negative x plus y when you put the negative out over 4. Well, this is good because now you have 2e to the x plus y plus 2e to the negative x plus y divided by 4, and then these guys cancel the same way like they did in the previous problem to get you what you're looking for. E to the x plus y plus e to the negative x plus y divided by 2. Yay. This is known as mathematical gymnastics. Is it hard? No. Is it tedious? Yes. Right? It's a lot of foiling and multiplication and worrying, especially if your brain doesn't explode when you are keeping track to add exponents and making sure you don't mess up on the minus signs that are in front of each, right? Because the minus sign over here and the minus sign there have nothing to do with each other, right? So, but you'll manage. Now, I want to jump to length of curve. Remember length of curve? We had that formula. I spotted a problem, and I said, I will have to go back to this problem, and I know everyone will love it. So I'm going back to 6.5 just to show a problem, which we're not going to do now, but a little later. But I just want to show a problem that was there for homework. Let me just find it. No coffee. Oh, there it is. It was staring at me. I couldn't see it. So, okay, so let me just go 150. Anything look familiar? On the list at this moment in time? Number 10. What is that? It's hyperbolic cosine, exactly. So they gave you the whole problem, and then you have to go and suffer and bleed and sweat, right? Working with ease and multiple terms and taking the derivatives. We're going to learn the derivative of hyperbolic cosine is hyperbolic sine. And you're going to stuff that in that square root, right? Rather than having all of this. Do you know when you square all of this stuff, how much mess is that going to make, right? It's going to be a lot of mess to do this. So you are going to replace all of this with just hyperbolic cosine. whose derivative is a joke, and you stuff that into that thing over there, and then under 1 plus derivative squared, and then you just use identity, and you are done in 2 steps. Right over here, you would be going right for a long time. So they want you to suffer first, and then they say, "Ha! You could have done this problem like this had you known hyperbolic equations, right? Functions." So you have seen hyperbolic functions in your homework, even in Calc 1. Any problem posed this way can be rewritten as hyperbolic cosine and done like that. But then, right, you can't learn everything at once. So now you can go back and redo some of your Calculus 1 homework and practice, and then redo problem 10 when you finish hyperbolic homework. So we have seen the basics of this, and now we have 6 hyperbolic inverse functions, which you get when you swap x and y and then solve for the y again. So if you have that y is equal to, let's say, sine hyperbolic x for the inverse, we have x equals sine hyperbolic y, and then if you hit both sides with sine hyperbolic inverse, whatever that means, we'll see what it means, but right, you will get that y is equal to sine hyperbolic inverse of x, and we call that inverse hyperbolic sine. Now, the derivation for this is given in the book. It takes some time and the knowledge of of logarithmic functions and hyperbolic functions in order for you to do this. I won't bother you with those derivations. Just want to see how far does it go. Okay, there they are. So on page 508, you get to find the inverse list. And if your hyperbolic functions were given with exponential forms with e to the x, then common sense is that the inverses will have ln's in them, right? That should be just common sense. So cosine hyperbolic inverse, and you don't have to memorize these formulas. I mean, they are not going to be used anywhere, and obviously if they pop up, you just look it up. So cosine hyperbolic inverse of x is ln of x plus square root of x squared minus 1 for x's larger than 1. So we had to have a restricted domain there. Sine hyperbolic inverse of x is the same thing, just plus under the root. So ln x plus square root of x squared plus 1. Tangent hyperbolic inverse, right, of x is going to be 1/2 ln of 1 plus x over 1 minus x for absolute x less than 1, so it works only between 1s. Cotangent hyperbolic inverse of x is going to be tangent hyperbolic inverse of 1 over x. for absolute x larger than 1. And then secant and cosecant are all in terms of cosine and hyperbolic and sine hyperbolic. So secant hyperbolic inverse of x is going to be cosine hyperbolic inverse of 1 over x for 0 less than x less than equal than 1. And finally, cosecant hyperbolic inverse of x is sine hyperbolic inverse of 1 over x, where x is not allowed to be 0. So this is the list of 6 trigonometric inverse hyperbolic functions. As I said, you do not have to memorize these formulas because you have plenty of stuff. I mean, if you go back to those identities, you know those identities one way or another through trig. You just have to make sure that you are not confusing the two worlds. The problem on an exam will say prove and the formula is given. So you just look at the formula. You absolutely must know that sine is e to the x minus e to the minus x over 2, and cosine is e to the x plus e to the minus x over 2. So you absolutely must know those two, and then obviously from the list of those 12 identities, the more you know, the better off you are. But the problem that would say prove will already have the full formula there, and that formula either works or it doesn't work. It's very simple. So at this point in time, I would just like to take a look at one more identity from homework. And then we're going to take a break. When we come back, part 2 of this lecture, a new video, which will be calculus of hyperbolic functions, where we do the derivatives and integrals of 6 plus 6, right? 6 regular and 6 inverse. So let's take a look at identities. This is absolutely beautiful. I mean, if you don't think this is beautiful, then you have no emotion. 2 sine hyperbolic of ln of secant x should be equal to sine x tangent x. That's problem 14. You're supposed to prove that this works. So the argument of sine hyperbolic is ln, whose argument is secant x. So now you have the trig and ln mixed in with hyperbolics all in one pile. Welcome to Calc 2. I hope you stretched before you came to class, right? So now we have to, what are we going to do?
Drop out.
Drop out.
It is an option.
It's always an option, right?
Yeah.
The easiest way out.
The window is right there.
You'll find him trying to catch them. Are we doomed? I mean, what are we going to do? Where do we start?
2 e to the ln of x? Or not?
Exactly. Very good. Replace sine hyperbolic with these, and the exponents are these ln's. then E is kill ln's, and you just have trig to massage to make left side equal to the right side. Great. So this is 2 times, and then it's divided by 2 because sine hyperbolic is E to the exponent. Now exponent is ln secant x. It's sine, so it's a minus. E to the minus ln secant x equals to sine x tangent x. So first 2 kills 2. That's done. Over here ln kills E. So you just have a secant x on the first one. Now the second one has this minus sign that it's pesky. So do we know what we do with that minus sign? This pesky minus sign right here. Because you can't cancel ln and E because of that minus sign, which is why I call it pesky. What do we do with it?
Drop the denominator.
You use the P rule, the power rule. P ln x is ln x to the P. So and that P is now -1 because it's just minus ln. So it's -1. So you have that as -1. So you have minus E to the ln of 1 over secant x because that -1 went inside. That needs to be sine x tangent x. So now these finally drop, whatever, and you have secant x minus 1 over secant x should be sine x tangent x, and now you are in realm of trig. The denominator, well, secant x is right 1 over cosine, so it's just cosine. Secant x, well, secant is 1 over cosine minus cosine, and that needs to be sine x tangent x. Did I mention the first class there's going to be trig in this course? I think I did. Oh, there it is. Common denominator now is cosine x, which you have 1 minus cosine squared x, because you need to multiply the second one by cosine over cosine. That still needs to be the sine x tangent x, and you hopefully see it by now. 1 minus cosine squared is, very good. And now this is where you split sine x times sine x over cosine x, which is sine x tangent x. Yes. An amazing problem to bring up Thanksgiving, or someone asks you, hey, how are you, what's new? Work it out for them right on the side. So good. That's our first half. When we come back in about 210 seconds, we are going to have the calculus part of hyperbolic, which are including derivatives and integrals. So see you then.